Hello everyone, welcome back to the channel uLearn Education Online.
Now we are here to discuss the concept differentiator circuit design using ideal op-amp. In this video, you are going to see what is differentiator and what are the types of differentiator circuits and how to derive the output voltage for the ideal differentiator circuit using operational amplifier, and also how the output waveform looks like for the differentiator circuit with the applying of different input signals. At last, we are going to see what is the frequency response of ideal differentiator circuit using op-amp, and what are the advantages of using this circuit and what are the disadvantages of using ideal differentiator circuit, how to overcome those disadvantages. Now we are going to see what is differentiator. So the unknown circuit or a black box circuit in which the output voltage obtained is the differentiation of input signal, then we can call this black box circuit as differentiator circuit. If you observe this equation, the circuit output voltage is differentiation of input. Okay, so now we are going to see what are the types of differentiator circuits. If this circuit is designed using passive elements, now what are the passive elements? Resistor, inductor and capacitor are passive elements. So if this unknown circuit is designed using RLC in such a way that it will provide the output voltage as a differentiation of input, then we can call it this as passive differentiator. Similarly, if this internal circuit is designed using active devices like BJT, FETs, MOSFETs and operational amplifier, then we can call this circuit as active differentiator. Now, we are going to see how to derive the output voltage expression for this active differentiator circuit. Okay, so for this differentiator circuit, the input is given to the capacitor C1, and here the resistor is connected across the feedback path of operational amplifier. Here we are considering that the op amp is an ideal case, which means that the virtual ground concept is applicable. Virtual ground concept means in the sense VD value will be 0 and the currents entering at both the input terminals of op amp will be 0. Okay, now since the VD value is 0, the node potentials at A and B are equal, means we can say that VA and VB are equal. Now we have to find what is the value of VB. Since this VB is connected to our compensation resistor, we are concluding that there exists some voltage. Okay, but here the VB is indirectly 0. Why? Because since it is seriously connected to this input of op amp non-inverting terminal, we know that the current entering at input of non-inverting terminal of op amp is 0, since the current flowing through our compensation resistor is also 0. So the voltage drop across this R compensation resistor value will be 0. So VB is indirectly 0 and therefore VA is also 0. Now simply apply KCL at node A. If you apply KCL at node A, then we can write the current flowing through the capacitor will be equal to the current flowing through the resistor. Okay, now here it is C1 into d by dt of VA minus VI plus VA minus V naught by RF is equal to 0. Since VA is 0, we can substitute this in this equation. Then we'll get finally equation as C1 into d by dt of minus VI, which is equal to V naught by RF. If you simplify this equation, finally the output voltage V naught we can obtain as minus RF into C1 into d by dt of input signal. So finally in this output voltage expression, we are obtaining a differentiation of input signal. Okay, here this RF into C1 is nothing but the time constant of a differentiator circuit, and the negative sign here indicates that there exists a phase shift of 180 degrees between input and output signal. So this is the procedure how to derive the output voltage expression for this ideal differentiator circuit. Next we are going to see how the output signal waveform looks like with different type of input signals applied. Now we will see how the output waveform looks like with the applying of input step signal to the ideal differentiator circuit. Okay, so for easy calculation of output voltage, assume that the time constant of the differentiator is unity, means Rf into C1 is equal to 1. Therefore, we can write the V naught of t expression as minus d by dt of Vi of t. Now this is a step signal that is applied to the input of differentiator circuit. Now we know that the step equation. So the step equation is Vi of t is equal to A for t greater than or equal to 0. Okay. Now we have to find out what is the output voltage of ideal differentiator circuit. From the mathematical expression, we write V naught of t as minus d by dt of Vi of t. Here the Vi of Vt value will be A. So we know that differentiation of constant is always equal to 0. Nothing but differentiation of step signal is an impulse signal. But in practical, in order to raise the amplitude from 0 to A, it takes a finite time. So during this finite time, the differentiator output will be a non-zero value. So in order to differentiate that some non-zero value will be present during the interval 0 to A, it appears in the form of a spike. So this is how the output signal looks like when the step signal is applied. Now see what is the second signal that is applied to the input of differentiator circuit. The second signal that is applied is a square input signal. So this is the square signal we are applying to the differentiator circuit. Now for this, if you write the mathematical expression, that is for t greater than 0 and t less than t by 2, the amplitude is plus A. Okay, and for t greater than t by 2 and t less than t, nothing but total time period, the amplitude is minus A. So this is the equation how we have written for the square signal from this signal shaping. If you observe, for 0 to t by 2, it is nothing but a step signal. Okay, so for the step signal, we know that a negative spike will be appear. Similarly, for t by 2 to t, a positive spike will be appear. It means here there exists a 180 degrees phase shift between the input and output signal because of negative sign that is present in the output voltage expression. Or else, if you know the basic property, that is the input signal is applied to the inverting terminal of op amp. See, whenever the input signal is applied to negative terminal of op amp, definitely the output voltage is having a 180 degrees phase shift between the input signal and output signal. Okay, now we are going to see the third signal, that is a sine signal. So here this sine signal, we are having different time intervals. Okay, so at each time interval we have to find out what is the output voltage value and how the shape will looks like. So let us consider the sine equation as Vm sin omega t. If you differentiate this equation, then it is Vm is constant, so d by dt of sine t is cos t, whereas here d by dt of sine omega t we can write as omega into cos omega t. Okay, so here write omega in terms of time period as 2 pi by t. So here at t is equal to t by 4, find out what is the value of v naught of t. Similarly, at t is equal to t by 2, what is the value of v naught of t, and at t is equal to 3t by 4, what is the value, at t is equal to t, what is the value. If you find out at different time intervals, this sine wave is converted to a cosine wave. Okay, this is how to find for the given input signal how the shape of output signal will looks like. At last, we are going to see how to find the frequency response of ideal differentiator circuit. So in this frequency response, we have to plot the gain frequency curve, means how the output circuit will respond for different frequencies. So for the high frequencies, how the gain will be, and for the low frequencies, what is the gain value we are going to calculate. So for calculation of gain, first we have to find out the ratio of V naught by Vi. After finding the ratio of V naught by Vi, we have to find out the relation between gain and the frequency. Thereafter, we calculate the magnitude. So from the magnitude, we are plotting the gain frequency curve. Okay, since for the ideal differentiator, we know that the gain expression V naught of t is minus Rf into C1 d by dt of Vi of t. So it is a time domain signal. We have to find out the relation between gain and the frequency. So we can easily convert this time domain expression to frequency domain expression by applying a Laplace transform. If you apply Laplace transform, so this V naught of t can be converted to V naught of s. Next, minus Rf into C1, it is constant, so it replaces as it is. And here it is differentiation of input. We know that in the Laplace transform, differentiation of input in time domain is multiplication of s domain into Vi of s. So we can write d by dt of Vi of t as s into Vi of s, and here we are considering only first order. Okay, and the higher order terms are neglected. So finally the s domain expression or the Laplace transform expression is V naught of s is minus Rf C1 into s into Vi of s. Now we can find the gain value, that is V naught of s by Vi of s is minus Rf into C1 into s. We know the relation between s and the frequency as s is equal to j omega. So simply substitute s as j omega in this equation. We will obtain V naught of j omega by Vi of j omega as minus j into Rf into C1, where omega is 2 pi f. Okay, so final expression of gain is minus j into Rf C1 2 pi of f. It is nothing but an imaginary term. Now in order to find the gain, we have to take the magnitude of this equation. Okay, so if you observe the magnitude of the equation, if you take, we can write the square root of real square plus imaginary square. Here the real square term will be 0, so the imaginary square is omega Rf into C1. Okay, if you calculate, then you will get finally the expression A is equal to 2 pi f into Rf C1. Now let us consider 2 pi Rf C1 as one constant. Let us consider it as an Fa. Okay, one unknown frequency, which is equal to 1 by 2 pi Rf into C1. So let's substitute this Fa in this equation. Finally we can write A as F by Fa. Okay, if we know that this Fa value is constant, why it is constant? Since the Rf and C1, the circuit resistance and capacitance is constant, so the Fa value will be constant. Here the F value will be increased. Okay, so if you observe from this graph, let us say that the F value is less than Fa, means the numerator frequency is less than denominator frequency, then we can say that the gain is decreasing. Okay, at f is equal to Fa, the A value will be constant, that is 1, so it represent a constant curve. At f is greater than Fa, the gain value will be increases. This is a numerical value. If you convert this equation in terms of dB, then we can write the gain in dB expression as 20 log A, 20 log of f by Fa. Okay, so we know that the log of denominator term, if it is high than numerator term, then the gain value will be negative and log 1 will be 0, and if numerator term is greater than denominator term, the log value will be positive. Okay, so if you consider this equation, at f is less than Fa, the gain value will be negative. At f is equal to Fa, the gain in dB is 0. Okay, log 1 value will be 0, so the gain at that point, at which frequency the gain is 0, we are calling that frequency as a cutoff frequency. So whatever the constant term that we have assumed, this is the cutoff frequency of differentiator circuit, and if f greater than Fa, the gain is positive. So this is the procedure how we have to plot the gain versus frequency curve. Here we are assuming that the gain is measured in terms of dB. Now if you observe, what are the disadvantages is, at higher frequencies, means at F is greater than Fa, the gain is constantly increasing, which means the op amp will goes into the saturation. We know that at the saturation point of an op amp, the output signal will be a distorted signal and the circuit will not be work in a stable mode. Hence the op amp will going to oscillate its system. We are calling it that system as an unstable system. So finally at higher frequencies the differentiator circuit will be act as unstable state. And also we know that from the capacitive reactance at higher frequencies the capacitive reactance will be zero. So it simply allows the high frequency component and also it allows the noise frequency components and amplify the noise signal, which is difficult to remove the noise signals when we are transmitting through a communication channel. So these are the two disadvantages of an ideal differentiator circuit. In order to overcome that two disadvantages of ideal differentiator circuit, we are going to modify the ideal differentiator circuit with adding of some parameters that we are calling it as a practical differentiator circuit. What how the frequency response of practical differentiator circuit will be considered and how the output voltage can be derived from the practical differentiator circuit we are going to see in the next video. Stay tuned. Thank you.